Hello and welcome to another video regarding applied electricity. So today we'll be talking about magnetic circuit. Now, why is this topic very important? It's because there tend to be a very interesting relation between current and then magnetic field. So let's say you have current passing through a wire. As a result of this current, there's going to be a magnetic field around the wire. So we have the magnetic field around the wire, and you can verify this by what? By placing, you place a cardboard, right? And then you have the current passing through a wire, then you place on it, iron filings, and the alignment of what? You see that the iron filing is going to what? To be arranged in a circular pattern. That indicates what? You're having a magnetic field passing through the wire. You can also indicate this by using a compass. The compass will also tell you that there is a magnetic field around the wire as a result of the current. And once we have our magnetic field, in order to understand the magnetic field, we try and look at some of the parameters that can be associated with the magnetic field that we have, right? And another way we tend to have a magnetic field is what regards to a bar magnet. For example, if you are here a bar magnet and you want to know the north and south pole, you suspend the bar magnet, right? And then the north second pole is going to face the north pole, and the south second pole faces the south pole. So you have north and south pole on your bar magnet, and around your bar magnet there's an area or surrounding whereby the bar magnet can attract other magnetic material. That is what we mean by magnetic field. Now, with our magnetic field, you can see that we have some invisible lines, right? Or some kind of imaginary lines that we use to describe the magnetic field. And that is referred to as lines of force, or we call them magnetic flux. A group of lines of force is referred to as magnetic flux. So once we have our magnetic flux, the unit, right, the symbol we use is what? The Greek letter phi, or can call it phi, and then the unit is Weber. So we use the abbreviation WB, best to Weber. And with our magnetic flux that we have, we can also get another important parameter, which is going to be what? Magnetic flux density, which is, we imagine that you place a surface, right, in the magnetic field, and you have these lines of force or magnetic flux passing through the surface. So the total number of magnetic flux passing through a defined area is what we refer to as magnetic flux density. So you have your lines passing through the surface, then that will give us the magnetic flux density. So it's magnetic flux over area, and the unit is Tesla. Now, with the magnetic flux density, we can also talk about another important parameter, which is magnetomotive force, or we call it magnetization force. And this is the force that causes the existence of the magnetic field around the wire, right? Anytime you have current passing through the wire. Now, how do I get this force, right? You can think about this force. For example, if I have a wire and current is passing through, mean the MMF, the force that is going to cause the magnetic field to be produced is going to be the current. So you can see that MMF is the same as what current. Now, if we state a copper, the same wire, but this time you roll the wire to form a number of turns, right? That means this time the magnetomotive force is going to be equal to what? The current times the number of turns you roll this up, right? That will current times and turns. That will give us the MMF. So the general formula for MMF is current times the number of turns. Now we can move on to another important physical quantity, which is magnetic field strength. if you have a magnetic field already and want to know how strong this magnetic field, we can define that by calculating the magnetic field strength. And the magnetic field is simple, but the magnetomotive force per the mean length of the magnetic flux path, right? So we have Fm over what? L. L here is the mean length of the magnetic flux path because you have magnetic field and you have flux in the magnetic field. So that mean length of that will give us the length. Yeah. Now, imagine we are dealing with the first one that I talk about, you have your wire, you load the wire to n number of turns. You can see that here, within the wire that I hold, there are space between them, right? I have air, right? I have an empty space there, and that's is regarded as what? Air gap, right? So if you have air gap, and now imagine you know the magnetic flux density and the magnetic field strength. If we were to divide this magnetic flux density over the magnetic field strength, you get the permeability of free space. And this is a constant value, and it's equals to 4 pi times 8 power minus 7 Henry per meter. All right. So we get this as a constant. All right. Now, if you are in other media other than air, what that means that here you can see this example, we have iron, right? So this time I acquired the wires are onwards a material, and this is iron. Now that I have such a diagram, that means if we were to take the magnetic flux density over the magnetic field strength, that will give you what? The absolute permeability of the material, and that will be relative permeability times what? Permeability of free space, right? So this has to do with the material. In this example, we have iron. So if you have iron there as your material, meaning if this can use a relationship, right? Now that we know how to calculate the permeability, especially the absolute permeability of any material that we may have, we can also talk about the reluctance of such materials, right? Any material at all is going to oppose the establishment of magnetic field on the material. That is what we refer to as reluctance. So reluctance is simply the opposition to the establishment of magnetic field on the material. So here you can see that if I have my iron, piece of iron, the iron is going to what? Resist the magnetic field that is going to be what? Produce on it. That is what we mean by reluctance. So every material has this reluctance. So we can see here, reluctance. We can now try and get the formula for reluctance in terms of what? The magnetic flux and the magnetomotive force. Now, when it comes to the magnetic flux, right? We know that once we have a magnetic field, mean you have magnetic flux in there. Then imagine if you increase the amount of the force, right? The magnetomotive force. You can see that the magnetic flux is also going to increase. So you are going to have a lot of lines of force in your magnetic field, which is a magnetic field. So magnetic flux is actually proportional to the magnetomotive force. This is similar to Ohm's law, whereby you have current passing through a conductor, right? It's going to be that proportional to the voltage applied. So you have current with that proportional voltage applied. So here too, you can think of the current as a magnetic flux density, and then the magnetomotive force being the voltage here. And then you have this. We introduce now our equal sign, and then we bring a constant K. That constant just the inverse of the reluctance. So we have reluctance being equals to what? Magnetomotive force Fm over the magnetic flux. Now we can expand on this idea and then see what we can get out of this. I can replace the magnetomotive force with what? HM, right? So because we know magnetic field is equals to what? Fm over L. So you make Fm the subject, you get one HL. And then when it comes to the magnetic flux, I can also make magnetic flux from the magnetic flux density formula. So how you make this? The subject, you get magnetic flux density times area. And then you can see here I have magnetic field strength over what? Magnetic flux density. And I know that magnetic flux density over magnetic field strength will give you the what? Absolute permeability, right? So I can write it here. So that will be what? Here's H over B. So that will be the inverse. So you have length over the permeability, absolute permeability times area, right? So that's the reluctance. And if we are dealing with air gap, so since an air gap, the relative permeability of air is 1, and it's 1 for any other non-magnetic material. So if you are dealing with wood or glass, meaning their magnetic permeability, relative permeability is also going to be 1, right? Now I can get this, the length over the permeability of it as area for air gap, right? This is for air gap. And when it comes to other media that are air, we take the length for the absolute permeability of absolute permeability times area. That will give us the reluctance. And this is how you can explain the magnetic field around a conductor, in this case a wire, anytime there's what? A current passing through the wire. So these are the parameters of the magnetic field. And in summary, we have magnetic flux density, magnetic field strength. Then we can talk about reluctance of the material. See you in the next video. Bye-bye.